Hey guys, welcome to our video for today. I wanted to make this video because I wanted to make sure that we get through this chapter. If you guys have any questions during the video, you are welcome to pause the video and ask questions in the chat, and I will answer them as soon as I can. All right, so today is Monday the 22nd. We are back after not having class for a week. So we did not do any assignments last week. I thought about sending you guys some stuff, but I figured you guys would enjoy some time off. And I didn't know if you guys had power or not. And so no assignments, no class, nothing like that. So today we're kind of starting again. We are going to finish chapter 13 today on chapter 15. I've got 13 written on my paper, but chapter 15 on acids and bases and equilibria. So on buffers. So today during class, I need you guys to complete the warm-up. I think it's 3 questions. And then I've got the exit ticket that it's going to be due by midnight tonight. The exit ticket is pretty easy. I did put the slides in there so that you can just look at it in one place and get it done quickly. And then I'm giving you guys homework problems on chapter 15, AP multiple choice questions from the book. These are going to be due on Sunday, so Sunday night. So they need to be completed when you come to class on Monday. Okay, and we can talk about them. Okay, I want to talk about our plan real quick. I think I changed our calendar. Maybe I didn't. Let me open a document and show you guys what our plan is here real quick. So where did it go? Oh, it went to my other monitor. Come on. If I don't have the monitor on, then I can't see it or move it. There we go. All right, so here it is. All right, so today we're going to finish chapter 13. Wednesday, we're going to start chapter 17 on thermodynamics. So we're going to be talking about a little bit about enthalpy again. We're going to hit enthalpy a little bit, but we're going to talk about some new concepts. We're going to talk about entropy, free energy, spontaneity, and how to predict whether a reaction will happen. Okay, so it's very conceptual, a little bit of math in there. I think we've done most of the math from this chapter, though. There's a little bit more math in here, but we've done most of it. So we'll spend about 3 days on thermodynamics, hitting it kind of quickly, and then Friday before spring break, we're going to have our exam over these 2 chapters, and it's mostly going to be this chapter. And I really just want to give you guys an exam over this chapter before you guys have 2 weeks off. And you forget everything, right? And so I want to assess where you guys are at that point, and then I am going to give you guys some assignments over spring break because you guys do have 2 weeks off. So we're going to cover gases. You guys are going to do a little lesson on gases, like in the NIMSY packet, and then I'm going to have you guys do some kind of a pre-AP review study guide kind of thing. Kind of reviewing bonding and atomic structure and things like that. Kind of get us ready for the end, because when you guys come back from spring break, we will be running out of time because spring break is the 8th through the 12th. One of these is spring break, one of these is intersession. We come back on the 22nd of March, and then we have almost 2 weeks left in March, and then it's April, and April is our last month before the AP test. I think the AP test is the 7th. I have to look. I can't remember, but it's that first week of May. So we are running out of time here. The week last week did kind of set us back, but I think we needed a week off. I think it was great. I hope you guys were able to stay warm and safe. All right, so let's jump right into our warm-up. Here's number 1. All right, so the table above shows the values of Ka for 4 weak acids. Which of the following pairs of chemical species, when combined in equimolar amounts, results in a buffer with a pH that's closest to 7.5? All right, and then A, B, C, D there are the answer choices. Okay, so these are multiple choice, and I did pull these from AP Classroom. So this one, and I don't know if I have enough room to write, but I'll try to write on here, but I think I'm going to need a, let's see what I can write on here. So we're going to need a pH. So the pH is closest to 7.5. So basically we want the pKa of the acid that we use, the weak acid that we use, we want the pKa of it equal to the pH. Okay, so let's look at each of these. Actually, I'm going to kind of write this in here. So we're going to take the Ka of each of these acids, and well, I'll show you a way to do this one. I don't really like it, but this is kind of my way to do it. We know that the pH is equal to 7.5, and we know that the pH is equal to the pKa. So what we can do is go ahead and find the anti-log of the pH, which is going to be the H plus concentration. That's going to be 10 raised to the power of negative pH, or 10 raised to the negative 7.5. You can see what that number is. We get 3.16 times 10 to the minus 8. All right, and so that number is going to be essentially equal to the pKa. Even though we found the H plus concentration, we find the pKa. Because remember, pKa is equal to the negative log of the Ka, just like pH is equal to the negative log of the H plus concentration, right? So if I find the H plus concentration, that will help me determine, well, kind of like I could find the H plus here. I can find the H plus concentration with this, 10 to the negative pH. We know that the Ka is equal to 10 to the negative pKa. Okay, and so I can just find the H plus concentration, and I know that it needs to be close to the pKa. So let's look back at the question. The H plus concentration and the pKa, or actually the Ka value, should be equal to 3.16 times 10 to the minus 8th, which is, that was our H plus concentration. So H plus concentration is equal to our Ka value. We can put molar there if you want. So we want to find the one that has 10 to the negative 8, and that's it. So that would be C. Okay. Now another way you could do this problem is just look at this table here, Ka. All right, so we have the Ka. pKa equals the negative log of the Ka. So we can plug that in, and let's see what we get. Negative log of 3.0 times 10 to the minus 8. When I plug that in my calculator, I get 7.5. So if you want a straightforward way to do it, that's fine. The other way, it makes kind of more sense to me, because you're given the pH, and I want to work from the pH. But you can also work from the answer choices back to find which one has a pH closest to 7.5, or a pKa closest to 7.5. And if this isn't making sense, please let me know, and I'll go through it again in class with you guys, okay? I'm going to try to get this video done within class time, but I doubt that I'm going to be able to get it short enough to where you can watch it in class. And so some of this you might need to watch after class, but not much, just a little bit, okay? And so if you guys have questions, we can talk about it next time, okay? Or after school. I'm definitely available after school. All right, number 2, a solution is prepared by adding 100 milliliters of 1 molar acetic acid, which is a weak acid, to 100 milliliters of its salt, so 1 molar sodium acetate. So we have a buffer solution here. The solution is stirred and its pH is measured to be 4.73. After 3 drops of 1 molar hydrochloric acid are added to the solution, the pH of the solution is measured and it's still 4.73. So the pH did not change, and that's because it's a buffer. Which of the following equations represents the chemical reaction that accounts for the fact that acid was added but there was no detectable change in pH? And so if you look at these reactions, think about what we have in species. We have HC2H3O2. We have HCl, which remember is just H plus or H3O plus. And so we're adding strong acid. Keep in mind that that strong acid here is going to react with, not with that, but it's going to react with the conjugate of it. It's going to react with this. C2H3O2 minus, that's going to react with H plus, or with H3O plus. Notice that it's H3O plus in every one of the answer choices, so let's say it's H3O plus. If we react those two together, then we get more acetic acid. So that is our answer choice here. H3O plus is going to react with the salt, the negative ion of the salt, and that's going to make more of our acetic acid. And since acetic acid is weak, that doesn't make the solution more acidic. It's going to store that H plus in the molecular acid form. And since that's a weak acid, it's not going to dissociate, and so we're not going to have any extra H plus in solution. Therefore, the pH doesn't change. Okay, easy peasy. That was a really easy one. Okay, number 3. I feel like number 1 was the hardest one. Number 3, we have 2 acids here. I forgot what this is called. I don't know what that's called. I have to look that up. Propanoic acid, maybe? Propanoic acid. So we've got this guy here with this Ka. We've got methylamine, which is a weak base, actually. This is its conjugate acid, and this is its Ka. So notice that this one is much weaker than this one. The acid dissociating constants of these 2 substances are given in the table above. Which of the following mixtures is a buffer with approximately a pH of 3? So how do we do this one? I'll try to write what I can on here. Remember that the pH is equal to pKa plus the log of the base over the acid, or the salt over the acid. I even like this formula a little better. All right, and so the pH is equal to 3. So again, I like to solve for the H plus concentration from the pH, saying, okay, it's 10 raised to the negative pH, which is 10 raised to the negative 3, which is 1 times 10 to the negative 3 molar. I know that that H plus value must be equal to the Ka. Okay. And so if we look at this one, that's closer to this value. Oops. It's not that close, but it's much closer than this one. Okay. All right. So what we want is we want an H plus concentration equal to 1 times 10 to the negative 3. Let's see, pH. And if we take the negative log of each of these, so if I take the negative log of the Ka, we get the pKa. The pKa for this guy is, let's see what we get there, negative log of 8.3 times 10 to the minus 4. I get 3.01 for the pKa of that guy. So that sounds nice. And negative log of 2.3 times 10 to the minus 11. Let me type that in again. Negative log 2.3 times 10 to the negative 11. We get 10.6. So obviously the pH, the pKa for this one is much closer to the other one. So we're going to basically eliminate any answer choices that have the other one in it. All right, and then the difference between these two, I'm not sure. What else did I do on this question? So we want a pH of 3, and so we want HC3H5O3. So 3.01. So let's do this. Let's do if the pH 3.01, let's do 10 to the negative pH, which is 10 to the negative 3.01. So let's take the pKa. So okay, if that's the acid, then the pKa of that acid needs to be equal to the pH. So the pH is 3.01. So I'll do 10 raised to the negative 3.01. I got 9.7 times 10 to the minus 4 molar H plus. So if we have that much H plus in solution, That's kind of close to here, but it's a little low. Oh, I see the difference here. Do you guys see the difference? Now I get it. If you look at these answer choices, this one has the propanoic acid in it. This one only has its salt. So we don't need the salt. We need the HC3H5O3. So it makes it look like it's a math problem, but it's really not. But we want to figure out which of these has a pKa closest to the desired pH. The desired pH is 3. And so the pKa needs to be close to, or the Ka value needs to be close to that. So we essentially pick that one, and so we find the one that has that and sodium hydroxide. Now I'm not sure. Let's see which mixture. So we've got some of this, and I'm trying to figure out why we need the sodium hydroxide. Let's take a look at that. Let me see if I can move this over to a different screen. Or maybe I can, let's see. Is it gone? Nope. Save. I don't know where it saves it though. That's the thing. Okay, whatever. Let's just do a whiteboard. I was trying to not lose my work there, but we lost it anyway. Okay, so we have, let's look at this answer choice here, C. 100 milliliters of 0.1. So let's start with that. There's my little man. So we've got, let me scroll down here. There we go. So we have 100 milliliters, which is 0.1 liters. So I'm going to multiply the volume by the molarity. The molarity is 0.1. All right. So we have 1 times 10 to the minus 2 molar CH3H5O3. So let's go ahead and set up a rice table. CH3H. What is it? HC3H5O3 is going to be in equilibrium with H plus this propoanate anion. Again, I think that's what this ion is. I have to check. Set up a rice table. The initial concentration is 1 times 10 to the minus 2. This is 0. We have from our answer choice, we have propanoic acid and the sodium hydroxide. We don't have this, so I'm going to put 0 here. We're going to put minus x plus x plus x. This is going to be 1 times 10 to the minus 2. We're going to get rid of the x, and then that's going to be x, and that's going to be x. All right, and then let's see what we get here. So basically 1 times 10 to the minus 2. I have to save this. I thought I had this problem completely worked out on paper. Obviously not. There's a lot of steps that I was missing. And I figured I was because I felt like I didn't understand this problem that well. So let's take our rice table. I'm going to clear the screen, and then we're going to do Ka. So Ka is equal to 8.3 times 10 to the minus 4. That's equal to H plus times C3H5O3 minus all divided by HC3H5O3, which is equal to x squared divided by 1 times 10 to the minus 2. All right, so now we're going to cross multiply, so that's over 1. So x squared is equal to the product of those two. 1 times 10 to the minus 2, multiply it by 8.3 times 10 to the minus 4. And we get x squared equals 8.3 times 10 to the minus 6. We square root that. And we get 2.88 times 10 to the minus 3. So that's H plus concentration. Okay. What's the pH of that? Negative log of that. So negative log of 2.88 times 10 to the minus 3. pH is equal to 2.5. All right, so here's what I was trying to get at. I wanted to determine the pH of just the weak acid. The pH of just the weak acid is 2.5, right? If we look back at our question, where's our question? Here it is. We want a pH with 3. So if we have 2.5, we can take this one. So this is our answer choice. 0.1 molar of the let's see. I'm trying to remember what the answer is here. From my notes, I can't even tell. I want to say it was C, though. Let me open AP Classroom and have a look. I didn't want to waste time doing this. I thought my notes were good, but they're awful. There we go. And let me find this question. Actually, I got an idea. I know how to find the answer a little better, a little easier. It's on Canvas. Let's look at this quiz on Canvas. Be faster. So we'll go to AP. Modules. 222 warm up. I think this is it. Edit. So this is the number 3. Number 3. What is the correct answer? B. Okay, so correct answer is B. All right, so let's look at it. Correct answer is B. So again, and I was right. Okay, very cool. So what we need, so the correct answer is here. And again, the reason that that's the correct answer is pretty much because the pH that we need, we want a pH of 3. This acid right here has a pKa value close to that pH. But again, the pH of that acid only is 2.5. It's a little low. And so if we add a little bit of sodium hydroxide, that will bring the pH up to 3. So it's going to raise our pH from 2.5 to 3. And if we went through the calculations, we could see what that would do. So we have 50 mils of 0.1 sodium hydroxide. So let's see what that would do. So 50 milliliters of 0.1 molar sodium hydroxide. And then what's our concentration of our acid? 0.1. So we have 100 milliliters of 0.1 molar. I want to just say HA, which is our weak acid. Okay, so I have that. So we're going to do 0.05 liters times 0.1. That'll give us our moles of OH. So that's 5 times 10 to the negative 2 times 0.1. So that's 5 times 10 to the negative 3 moles of OH. And then I have 100 mils times 0.1, which is 1 times 10 to the minus 2 H plus. And so we're going to subtract this out. We're going to end up with more acid left over. So we're going to subtract 5 times 10 to the minus 3 minus 5 times 10 to the negative 3. That's going to get us 0. So essentially, you're going to make a BCA table subtracting out this 5 times 10 to the negative 3. So what is that? 1 times 10 to the minus 2 minus 5 times 10 to the minus 3. All right, that's, wait, what? 1 times 10 to the negative 2 minus 5 times 10 to the negative 3. I get 5 times 10 to the negative 3 moles of H plus. We're going to divide that by our total volume, which is going to be 0.15 liters. It's going to be this plus this. So 5 times 10 to the minus 3 divided by 0.15. Our molar concentration of H plus after neutralization is 3.3 times 10 to the minus 2. And so the negative log of that is our pH. So let me check something here. So 50 plus that divided by 1,000. 0.15, that's right. So 5 times 10 to the minus 3 divided by 0.15. All right, then I'll take let me store this value. Take the negative log of that value. I'm getting a pH of 1.477 after it's neutralized. Just really low. And then I guess we need to do the Rice table. Plug this concentration into the Rice table and then see what we get. So let's do that. So I got 3.33 times 10 to the minus 2. So let's plug that in the Rice table. So HA, H plus A minus. We're going to have 1 times 10 to the minus 2 molar here. This is going to be 3. Actually, this is going to be 3.33 times 10 to the minus 2 molar. This is going to be 0. So this is going to be minus x plus x plus x. And so we're going to have 1 times 10 to the minus 2 molar. We're going to get rid of the x. We're going to have 3.33 times 10 to the minus 2. We're going to get rid of the x. Then we're going to have x there. And then Ka equals 8.3 times 10 to the minus 4 is equal to this. So this is 3.33 times 10 to the minus 2 times x divided by 1 times 10 to the minus 2. Okay. So I'm going to do 8.3 times 10 to the minus 4 times 1 times 10 to the minus 2. I'm going to multiply these two together and cross multiply. So when I do that, I get that. Let's what is this in scientific? 8.3. 8.3 times 10 to the minus 6. And that's going to be equal to the 3.33 times 10 to the negative 2 times x. So I'm going to divide both sides by that 3.33 times 10 to the minus 2. All right, so I'm going to do that divided by 3.33 times 10 to the minus 2. Okay, and so I finally get x equals 2.49 times 10 to the minus 4. And what's the negative log of that? .6. pH equals 3.6. So that'll be the pH after everything's done. So it seems a little high. But essentially, we picked that answer choice because the pKa of the acid right here, the negative log of this value, is close to a pH of 3. Again, it's going to be a little low, and so we're going to need some of that sodium hydroxide to add to it. Okay. I hope you guys can follow that. I apologize. All right, so let's talk about how to prepare a buffer. Let me actually open these PowerPoints here. They're a little better. All right, so a chemist needs a solution buffered at a pH of 4.3 and can choose from the following acids. Okay, so here's our different acids. And so we want to determine which of these, which system will work in order to get a pH of 4.3. So how do we do this? Well, we know that a pH of 4.3 corresponds to an H plus concentration. We're going to take 10 raised to the negative 4.3, and we get 5 times 10 to the negative 5. And if you look at this, you can see that that's close to B. Wait. Actually, it's closer to C. 6.4 times 10 to the minus 5 is closer to 5. So benzoic acid is the one we're going to pick. Okay. So that's the way that I like to solve these problems. That's actually how the book is showing you the solution. So this totally works for me. We can see that this value is closest to this value. Now you could take the negative log of each of these Kas and then see which one is closest to 4.3. That would totally work too. Okay. Now it does say calculate the ratio of HA over A minus. I don't think I did that here. But the ratio would need to be equal to 1. You have maximizing buffer capacity when HA over A minus is closest to 1. Okay. When those are equal, because you want to have both ends. You want to have something that can soak up the acid and make more of the weak acid, and you want something that can soak up the base. So you want both. Okay. Oh, here's the answer here. Okay. So here's the H plus concentration. We can see that the this one, like I said, this one is closest to what we had for our H plus concentration. And look at our ratio here. It's closest to 1. So you want the one that has a ratio that is closest to 1. All right. And make sure, let's read this this thing down here. So we can use this formula here. Since Ka values rather than pKa values are given for various acids, we can use this equation to calculate the ratio of those two. Okay, so this is a very useful equation. I remember, I think it was Pei that had pointed this one out from the NIMSY notes, so good job there. This is a very important equation to use that I overlooked. Since the HA over A minus for the benzoic acid is closest to 1, the system, I can't read this. The system of benzoic acid and its sodium salt will be the best choice among those given for buffering a solution at pH of 4.3. This example demonstrates the principle that the optimal buffering system has a pKa value close to the desired pH, and the pKa for benzoic acid is 4.19. So remember, we wanted a pH of 4.3, so 4.19 is close to that. Awesome. Okay, so back to chapter 15. I wanted to hit a couple things. Remember that a buffered solution is a solution that resists a change in pH. So if we add strong acid or strong base, it will minimize that change in the pH. Remember that it consists of a weak acid and its salt, or a weak base and its salt. So here's some examples of that. I kind of wanted to just kind of get you guys back up to speed. Buffering capacity is the amount of acid or base that can be absorbed by a buffer system without a significant change in pH. All right, and so we're always looking for the, we don't really calculate buffer capacity. I haven't seen any questions like that where you calculate it, but we want to understand what it is, and we want to know how to get the maximum buffer capacity. And again, that's where the pH is equal to the pKa of the acid system that you're using, and the ratio of the acid to its conjugate salt, anion, when the ratio of those is 1. You have a ratio of 1, and we'll see that again. All right, so one way to calculate pH of a buffer system is the HH equation. pH is equal to pKa plus the log of the base over the acid, or the salt over the acid, or A minus over HA. Here's some hints for solving buffer problems. I wanted to remind you guys about titrations. The titrant is the solution of known concentration that's in the burette. So I just wanted to look at some of these. So this is a titration for strong acid, strong base, and so the equivalence point is 7. All right, and then remember the half equivalence point is right there. The strong acid, strong base. This is really easy. The pH is easy to calculate because all reactions go to completion, and so we just use our formulas to determine that. We don't need a Rice table or anything like that. No Ka problem. So this is what that would look like. Up until this point, we have only strong acid left, and then we have a neutral salt, and then we have strong base left after the equivalence point. But notice for strong acid base, it's a tug of war, and so they're going to reach 7. They're going to neutralize and cancel out. Now, if we have a weak acid, strong base, then the equivalence point will be shifted to the base side of things. And we're going to have a point that's called the half equivalence point, where the pH is going to be equal to the pKa. And the Also at the equivalence point, HA will be equal to A minus. These two will be equal. Okay. So here's the pH curve. Notice that the pH equivalence point pH is 9, so it's above 7. So since this is a strong base and a weak acid, the base is going to win a little bit, and we're going to make a basic salt in solution, and so that salt is going to hydrolyze water, making it basic. So that's why it's a 9 here. And so first we have a weak acid, so Ka only, and then we're going to have to neutralize some of that added acid as we titrate with the base. We're going to have to neutralize that base first. We're going to have a half equivalence point where these two are equal and the pH is equal to pKa. And then we're going to continue adding strong base until we reach the equivalence point. At the equivalence point, we're going to have a basic salt, and it'll be a Kb problem where the Kb is for that basic salt. In this case, that would be sodium acetate, NaC2H3O2. And then after we add enough base, now it's just a base problem where we're going to do negative log of the concentration of the base. Okay. All right, at the equivalence point, a basic salt is present and the pH will be greater than 7. After the equivalence point, the strong base will be the dominant species, and a simple pH calculation can be made after the stoichiometry is done. Here's the curves for a bunch of different acids with different Ka values. You can see how they change. So the smaller the Ka value, the lower it is on the pH scale, and then the higher it is. Actually, the smaller the Ka value is up here, and that should make sense. The smaller this value is, or the larger the value this is, the stronger the acid. The stronger the acid, the lower the pH. That should make sense. Okay, here's a pH titration curve for a diprotic acid where you have multiple inflection points with different equivalent points. So we have titration 1 here, and then titration 2. If you have a weak base, strong acid titration, it's going to be the exact opposite. Notice that the equivalence point is going to be on the acidic side of things. All right, and so we can label our points here. All right, so we start off with a weak base only, and then we add some of that strong acid that's going to neutralize. So it's still going to be a stoichiometry problem plus Kb, because you're going to have that weak base hydrolyzing water to make it basic. And then at some point, you're going to have the H plus equal to OH minus. You're going to have equivalence, and that's going to be a little bit acidic here because the acid will be stronger. And then after that, you're going to add strong acid, and so the pH will be the negative log of that H plus concentration. Okay, and here's an example. Ammonia getting hydrolyzed. Ammonia is titrated with a strong acid. So I wanted to show you guys a weak base that's titrated with a strong acid. So here's the Kb for ammonia. First, we determine moles of each species. We do our neutralization. We calculate the concentration of each of these after neutralization. That's what we have here at the bottom. All right. And then this says weak base plus conjugate acid, which means this is a Kb problem. The base is weak, and so we need to set up a Kb expression for that and solve for the sulfur X, which will be our OH concentration, and then find the pH from that. So the pH of this system will be 9.86. Okay, acid-base indicators, finally some new stuff. All right, well, I apologize for the delay, but here is some new stuff finally. So acid-base indicators are substances, usually weak acids, that you put in a solution, and it will indicate the pH. All right, so for example, actually mustard is a acid-base indicator. You can take mustard, or not mustard, but turmeric acid, turmeric, which is a spice. So you can take turmeric, which is yellow when you buy it at the store. You can put it in a solution, I think acidic solution, and it'll turn red. So an acid-base indicator is any substance that changes colors when it's in an acid or a base. Okay, and so at this point I'll start trying to show you guys the Rainbow Lab if I haven't already. I don't know if we did the Rainbow Lab. Let me know if we did that. I don't know if we did that one yet, and if not, we need to do it. That one is awesome. So we'll try to do that one here soon. Maybe we could do that right before spring break. So the end point is the point in the titration where the indicator changes color. And so there's some point, some pH where the indicator will be changing colors. All right, so when you choose an indicator, we want to choose an indicator that has an endpoint and the titration equivalence point. We want those to be as close as possible. Since strong acid, strong base titrations have a large vertical area, color changes will be sharp and a wide range of indicators can be used. However, for titrations involving weak acids or weak bases, we must be more careful in choosing our choice of indicator. So I'm going to kind of show you guys how you're going to pick an indicator. Like I said, indicators are usually weak acids, and they have the formula, the kind of the general form H plus In, where In is the whatever the structure of the compound is, whatever formula it is, it's going to be that formula plus an H. So that's going to be the molecular form of the acid, right? Before dissociation, they have one color when they're acidic, and they're in their undissociated state. And then they have a different color when they're in their basic state. So after it disassociates and forms the conjugate base, it's going to change colors. A very common indicator is phenolphthalein, which is actually kind of hard to spell. Phenolphthalein is colorless. So it's colorless when it's in an acidic or neutral pH. So if you take phenolphthalein and add some drops to it to a solution, if that solution is acidic or neutral, it will be colorless. But if you add base to it, it will turn pink, and it'll change pink and stay pink once it is in a basic solution. So the color will change in the range of 8 to 10. So if you take a solution, put phenolphthalein in it, let's say pure water. Take some pure water and put phenolphthalein in it, and it'll look like what we are showing in the bottom left. It'll look like this one. Let me get my pen back on. So it'll look like this one, okay? So this is phenolphthalein and a anywhere from a pH to 1 to 7. So that means it can be up to 7, but not greater than 7. Once the pH is greater than 7, especially if it gets all the way up to 8, you're going to start noticing a color change, and it's going to turn pink. And I've shown you guys the titration for that, and maybe I can show you guys the link for that, and we can watch that again so you guys can understand indicators. But this one will turn pink when it's 10. And actually, you don't want to, when you do a titration, you don't want a dark pink color. You want a light pink color, because a dark pink color indicates an excess of a base. So it indicates an excess of hydroxide ions. You don't want that. You want it to turn a pale pink color to show that the color has changed and you reach neutralization, but you didn't go past it. If you have a dark pink color, that means you've gone past it and you've added excess base, and so that's not an accurate titration. You want to just reach that equivalence point. All right. And when you do this in lab, it's very annoying to try to get it to perfect equivalence point. You have to be very careful. Here is the molecular structure of phenolphthalein. So this is the H form. So basically notice that this one has an H here, and this one, the H is gone. All right. The rest of the formula really doesn't matter. These are benzene rings. Basically, and this is colorless, and then this is pink. Usually 1/10 of the initial form of an indicator must be changed to the other form before a new color is apparent. So we're going to see a color change when 1/10. This will become important a little later in our notes. So usually 1/10 of the initial form of the indicator must be changed to the other form before a new color is apparent. Okay. The useful range of an indicator is usually its pKa plus or minus 1. So if you find the pKa of the acid, that's going to be the pH, and it's going to be plus or minus 1, okay? So somewhere close to that pH. When choosing the indicator, determine the pH at the equivalence point of the titration, and then choose an indicator with that pKa, with the pKa that's close to that. All right, so if you want to do a titration for a strong acid, strong base, which is going to have an equivalence point of 7, you're going to want to use a indicator that has a pKa close to 7. If you have a strong acid, weak base, you're going to have more like a pH of 5. You're going to need to pick an indicator that has a pKa close to 5. If you have a weak acid, strong base, let's say this will be 8, you're going to need a pKa close to 8. So you pick the the indicator that has a pKa close to your equivalence point. Sorry, I keep yawning. So here is a chart with different indicators. Notice that crystal violet is one that has a pH range of 0 to 1. It turns from like a yellow to a green to a blue. Then there's Cresol red, which has, I'm not sure why it has 2 of these, but between 1 to 2 it'll change colors, and then between 7 and almost 9 it'll change colors. Let me think of some. So crystal violet's an important one in kinetics experiments. And when we go back and review kinetics, I'll try to show you guys the crystal violet lab there. Phenolphthalein is down here. It's a basic one, so we don't see anything until we get up between 8 and 10. And that's important for you guys to know that phenolphthalein is 8 to 10. So you can pick a different one that has a different pH value. And so you can replace this with pKa. So if you look up the pKa's for each of these indicators, then you can pick out which one you want to use for a given scenario. Okay, here's a pH curve for titration with strong HCl, strong acid, strong base, and you can see that the equivalence point is kind of right in the middle. So phenolphthalein is used up here. Methyl red is used for acidic titrations. So maybe we could say this. Maybe we could say methyl red is used for strong acid, weak base. Phenolphthalein is good for weak acid, strong base. So the opposite. And then, of course, in the middle is going to be our equivalence point. So if you have a weak acid, strong base, you're going to use phenolphthalein. If you have a strong acid, weak base, and methyl red, it's pretty common. Now, if you had a neutral solution, if you look here, these are the ones that'll work for that. So pH is 7. So I'm going to circle pretty much these guys here. So alizarin, bromothymol blue, phenol red, or that one. And actually, I think bromothymol blue is very common for a neutral pH. Not purple, bromothymol blue. That one. That one's pretty common for a neutral pH. It goes from a clear to a yellow to a blue. Now, there is also a universal indicator, which I don't see in here. Where is universal indicator? Universal indicator changes colors from a blue to a pink. And now that I think about it, I think I did show you guys the Rainbow Lab. I think I found a video and showed you guys. All right. So we did that one. Now here's a pH titration with weak acid, strong base. Notice that the equivalence point is up in that phenolphthalein range, like we said. All right. Now how do we calculate Ka? So here's an example, and I think this is our last example here, guys, so bear with me. So a chemist is going to synthesize an unknown kind of new acid. It's a monoprotic acid where there's just one H that disassociates, and he wants to determine his Ka value. To do so, he's going to dissolve 2 millimoles of the solid acid and 100 milliliters of water, and then he's going to titrate the resulting solution with 0.05 molar sodium hydroxide. After 20 milliliters of sodium hydroxide has been added, the pH is equal to 6. What is the Ka of the acid? All right, so remember that millimoles is moles, but basically you can just divide by the volume. So you can take millimoles and put it in the BCA table, and then later you can divide that by milliliters, and the milli will cancel out and give you molarity. Okay, so you can use millimoles. It just means thousandth of a mole. Milliliter means thousandths of a millimeter means thousandth of a meter. Millimole means thousandths of a mole. So if you want moles, just divide it by 1,000. So it's easier to work with instead of a tiny, 1 times 10 to the negative 3. All right, so the first step is to neutralize the added titrant base. All right, so here's our neutralization reaction. We're going to have our conjugate acid, which we don't know the formula of it is. We're going to react it with that added strong base, and we're going to neutralize it. So we're going to subtract 1 millimolar from both sides, or from both substances here. We're going to add it to the products. And then we're going to divide that by the volume to get our concentrations. So first step is to neutralize the added titrant base, just like we would in a titration problem. Step 2 is determine the concentrations after neutralization. So we take the 1 millimoles, and you guys can see here that if you take the millimoles on top and divide by milliliters, leaving them in milliliters, you get molarity because milli cancels with milli. So all of the little m's here cancel. Just like that. All right, Livinus moles per liter, which is molarity. And then we're going to have very close to 0 molar H+. Maybe it won't be exactly 0, but very close to 0. So maybe we can do that. Very close to 0. Okay. Step 3 is to determine the equilibrium concentrations using a Rice table. So we plug in our concentrations of each of our substances. Again, this is 0. We have 8.33 times 10 to the minus 3 for our acid and its conjugate salt. Remember the X is negligible, so we can actually get rid of them. We're going to get rid of that X there always. And so it's just going to become 8.33 times 10 to the minus 3 for that one and that one. Now we're going to set up a Ka expression and solve for X. Ka is equal to the H+, so the ions, divided by the molecular acid in undissociated form. And then we solve for that. And the value for X is equal to 1 times 10 to the minus 6, which is equal to our H+. Okay. So pH is equal to 6. All right, so remember that the pH is equal to 6 after neutralization. And so we know that since the pH is equal to 6 after neutralization, right, it says that in the question. Where does it say that? Right there. pH is equal to 6. We can take 10 raised to the negative pH, and we get 1 times 10 to the negative 6. Okay, so we can see that the pH, notice that the H+ concentration is equal to the Ka, and notice that the pH is equal to the pKa. So this is a special point in our titration curve. This is called the half equivalence point. All right, the pKa is equal to the pH, and then also remember that the HA is equal to the A minus. All right, and so what is the Ka for the acid? 1 times 10 to the minus 6. All right, so 1 times 10 to the minus 6 is the Ka for our unknown acid. And the pKa for this unknown acid or newly discovered acid is going to be 6.00. Okay. Oh, we've got another one here. I'll just go through this one real quick. So indicator color change. Bromothymol blue, which is an indicator with a Ka value of 1 times to the negative 7. Notice that the pKa, notice that the pKa of that is equal to 7. So if the Ka is equal to this, then pKa is equal to the negative log of that, which is 7. It's yellow in its undissociated form and blue in its dissociated form, so when it's in its basic form. Suppose we put a few drops of this indicator into a strongly acidic solution. If the solution is then titrated with sodium hydroxide, at what pH will indicator color change first be visible? So for bromothymol blue, we know that the Ka is equal to 1 times 10 to the minus 7, and we know that Ka is equal to this. And so what we're going to do is we can assume that the color change is visible when the ratio of the base to acid is 1/10. So we're going to replace that in our formula here. So here's our formula. I replaced the A minus with 1. So remember that we want A minus equal to 1, and we want HA equal to 10. All right, so A minus over HA equals 1/10. All right, and so we're going to plug that in. Let me double check, make sure I put that right. Yeah. Yeah, N over HAN. Yeah, okay. And so we solve this for H+. So 1 times 10 to the minus 10, or 1 times 10 to the minus 7 times 10 is 1 times 10 to the minus 6. And then H plus times 1 is just H plus. So H plus is equal to this times 10, which is 1 times 10 to the negative 6. So H plus is equal to 1 times 10 to the negative 6. And the pH is 6. So the color change is going to be visible at a pH of 6. Ain't that nice? Okay, now we could also use the HH equation and get the same result. Now I do want to point out that when a basic solution is titrated instead, so this example, we had an acidic solution that we were titrating. So the bottom note here at the bottom of this screen is for when you are titrating a basic solution, it's going to be the opposite. So when a basic solution is titrated, the indicator HIN will initially exist as the base in solution, but then as you titrate with acid, more of the HIN will form. So the ratio will be inverted. So instead of 1/10, it's going to be 10/1. And so if we had this example, instead of getting a pH of 6, we're going to get a pH of 8. So that's just a note for when a basic solution is used. All right, guys, that is all I have. Thank you for bearing with me. I'm sorry that this was so long. Make sure you guys complete the warm-up and the exit ticket. I did make the exit ticket very easy, so make sure you guys complete the warm-up and the exit ticket today at some point. And then between now and Sunday, let's complete the AP multiple choice practice problems. All right, thank you guys so much.